Welcome to NGVEX Explainer.
Hey everyone, and welcome to the Explainer. Today we're diving headfirst into the really fascinating engineering history of laser welding aluminum. Now, for literally decades, engineers were completely stonewalled by some fundamental material challenges when they tried to join aluminum using your standard thermal processes. It was a headache, to put it mildly, but through sheer grit and continuous innovation, those walls eventually came down. So we're going to unpack exactly how the industry pivoted from those massive early struggles all the way to the absolute cutting-edge automated manufacturing setups we see today.
Real quick, here's our roadmap for the Explainer. We'll kick things off with the initial aluminum challenge, look back at the early CO2 laser era, and then explore those massive solid-state breakthroughs. After that, we'll cover modern technologies, look at some real-world industry applications, and wrap it all up with a summary and key takeaways.
All right, let's jump straight into Section 1, the Aluminum Welding Challenge. So, why exactly has aluminum historically been such an absolute nightmare? An engineering antagonist, really, in traditional fusion welding? Well, before we get into the heavy metallurgical answers, just think about its basic physical properties for a second. How does a piece of aluminum actually react to intense heat and blinding light? Well, here's the harsh reality of what happens when you blast aluminum with intense energy. First off, it has insanely high surface reflectivity to infrared light. It literally just bounces the laser energy right back in your face. Second, it has extremely rapid thermal conductivity. Basically, it acts like a giant heat sink, aggressively pulling the heat away from your weld zone way faster than you can pump it in. And third, and this one's a huge deal, the low boiling point elements mixed into the alloy, like magnesium, will actually vaporize before the rest of the metal even melts. They essentially boil away, leaving these hollow, empty pockets behind. So when you try using traditional thermal processing parameters, this brutal combination leads to a super high risk of solidification cracking, severe porosity, and nasty blowholes. It was honestly an absolute nightmare for early engineers.
Moving on to Section 2, Early Lasers, the CO2 Era.
Looking at the historical timeline here, the 1960s brought us the inception of the laser and the early use of CO2. By the 1970s, we had these multi-kilowatt continuous wave CO2 lasers that were absolutely fantastic for deep, narrow keyhole welding on carbon steels. But, and it's a big but, they completely and fundamentally struggled with aluminum. The industry literally had to sit on its hands and wait until the 1990s for diode-pumped Nd:YAG crystal lasers, and then the 2000s for high-power fiber and diode lasers to finally crack the code.
Okay, so what was the actual root cause of the CO2 laser completely failing with aluminum? It all comes down to one thing: wavelength. Gas-based CO2 lasers operate at a wavelength of 10.6 microns, and aluminum is highly reflective at that relatively long wavelength. But look at solid-state lasers, they operate at around 1.06 microns. Because absorption increases as the wavelength decreases, aluminum absorbs roughly 3 times as much laser energy at 1.06 microns as it does at 10.6. Using those old CO2 beams was practically like shining a flashlight at a mirror and expecting it to melt.
Which brings us nicely to Section 3, Solid-State Laser Breakthroughs.
What's genuinely fascinating here is the massive jump in electrical efficiency that comes right alongside that wavelength shift. Legacy CO2 gas lasers, they sit at a pretty dismal 10% efficiency. But as soon as we move down to solid-state mediums, like fiber, YAG, disc, and diode, they all neatly cluster around that magic 1-micron wavelength range, and their efficiencies just completely skyrocket. Diode lasers hit the highest efficiency at around 45%. This shift was the game changer. It solved the fundamental absorption barrier and finally provided enough power density to give us a stable, deep keyhole weld in aluminum.
Let's look at Section 4, Modern Aluminum Welding Technologies.
Just take a look at the striking difference between these two weld beads. That single-beam laser weld on the left is highly irregular, mostly because of aluminum's volatility that we talked about earlier. But if you use a dual-beam setup, where the laser is split in tandem, which you can see on the right, it massively improves the surface quality. This dual-beam approach is brilliant. It cuts down on centerline cracking, prevents underfill, and totally smooths out those irregular beads. It just delivers an incredibly clean and stable process. Okay, Section 5, Advanced Industrial Applications.
Seriously, just marvel at the sheer scale of this automated cell. Thanks to the high-power solid-state lasers we've been discussing, robots are now routinely welding aluminum components anywhere from 0.5 to 4 millimeters thick in standard automotive fabrication. And they aren't exactly taking their time either. These industrial solid-state setups are executing absolutely flawless fusion welds at speeds exceeding 10 meters per minute. That is incredibly fast. Now, to hit speeds like that, you need mind-blowing precision, which brings us to remote laser welding. This technology combines that multi-kilowatt laser, an industrial robot, and a highly advanced scanner mirror system. So, rather than physically dragging a heavy weld head to every single joint, the scanner just rapidly reflects and steers the beam itself. This slashes the non-productive time between individual welds down to mere fractions of a second. It massively boosts overall production cycle efficiency, and it does it without sacrificing an ounce of weld integrity.
But hey, what happens when you need to join totally different thicknesses of aluminum without warping the whole thing? Well, the solution is fabricating what we call tailor-welded blanks. By using two-sided simultaneous diode lasers working together, you can perfectly optimize the seam geometry. This manages the thermal load beautifully to prevent hot cracking, and it actually allows completely different sheets of aluminum to act together as a single, incredibly strong component. It's really elegant engineering. And laser technology isn't just about joining two flat sheets together. It's also used for building up new material from scratch. In laser deposit welding, sometimes called direct metal deposition, a laser beam rapidly heats the surface while a filler wire, or sometimes a powder, is fed directly into the molten pool, all under a protective shield gas. Because of the rapid heating, rapid cooling, and totally precise energy control, we can create metallurgically bonded layers perfectly suited for repairing surface defects, or even better, for additive, near-net shape manufacturing of brand new parts.
All right, wrapping things up with Section 6, Summary and Key Takeaways.
Let's quickly recap the main things you need to take away from today. We started with the basic problem. Aluminum's crazy high reflectivity and rapid thermal conductivity originally caused extreme weld defects. Early CO2 lasers running at 10.6 microns simply lacked the necessary absorption to efficiently couple with the aluminum at all. The massive game-changing shift happened with solid-state mediums, like fiber and diode lasers, operating at around 1.06 microns. That shift solved the fundamental absorption barrier completely. And today, that high power density gives us stable keyhole welding at speeds over 10 meters per minute, allowing remote, dual beam, and deposit welding techniques to absolutely dominate modern automated assembly.
Before we go, I want to leave you with one final kind of provocative engineering thought. As our solid-state electrical efficiency keeps climbing up toward 45%, and as our beam shaping and scanner technologies get even more precise, will additive laser deposit welding eventually become so efficient that it renders traditional subtractive manufacturing of aluminum entirely obsolete? Are we going to stop cutting away waste entirely and just start printing high-strength aluminum parts purely out of lasers and wire? It is a truly fascinating future to look forward to. Thank you so much for joining me for this explainer. Keep asking great questions, and I will catch you next time.
If you enjoyed this video, don't forget to like, subscribe, and turn on the notification bell so you never miss our latest engineering explainers. Thanks for watching, and I'll see you in the next video.